want to share my views and ideas that I share, that you have given me an opportunity to do that. Thank you very much for that. And now I move on to my presentation that is on chromatic numbers and its applications. So I organized my lecture. Uh, I organized my lecture in few sections. That is, first, we have a brief introduction or a simple introduction about the origin of graph theory and some of the basic elementary graphs, that is basic elementary graph structures. Then I move on to my coloring topic, then how we are going to color a graph, the second part. And in the third part, we will see some applications of coloring. And finally, we will have some real life applications, as well as I will take some of the theorems which we have done on coloring. So that will be the concluding part of my session. So to begin with, I start with the origin of graph theory. So how a graph theory originated, or how the graph is originated. So the slide begins. So this is the origin of graph theory. Graph theory, the first problem in graph theory dates to 1735, and it is called Seven Bridges of Königsberg. So here, this is the basic problem, how graph theory originated. So here, in Königsberg, there were two islands. They are connected to each other and mainland by 7 bridges. So there is an area called Königsberg. Here you can find two islands. They are connected to each other they are connected to each other and a mainland by 7 bridges. So the figure will illustrate this example. So here you can see there are two bridges, two islands, A and B. And here this A and B are connected by 7 bridges with the mainland. The mainland area is D, C, and here you can see the bridges. That is, A has one bridge to C, and then one bridge to D, then A has one bridge to B. Similarly, B has 5 bridges. You can see it from the figure. That is, B is connected to D with 2 bridges, and B is connected to C with 2 bridges, and B is connected to island A by a single bridge. So this is an area that is called the Königsberg Bridge and their graph. So here, the graph equivalent, or we have constructing this bridge problem, Königsberg bridge problem, into a graph. So in the side, you can see a graph where A is a point having, that is A is island, that is represented by a point. Then B is the second island, that is represented by a point B. So here, B is connected by 2 bridges to C. Here you can see 2 edges, that is 2 bridge. C is connected with 2 lines. Similarly, B is connected to D by 2 bridges. You can see B is connected to D and B is connected to D by the other bridge, second bridge. Similarly, island A is connected to island B by a single bridge, and island A is connected to C by a single bridge, and A is connected to D by a single bridge. So this is what a graph. So here we have formulated, or the basic problem or the origin of graph theory begins with a single begins with the problem of Königsberg bridges. So this is what the graph equivalent to the bridge. From the second slide, we can see the question. The bridges of Königsberg and the graph, we have seen it in the earlier slide. So this is the slide, the island, 2 islands, and its equivalent graph. This then I move on to the next slide. The question is, which made it way to Euler? So Euler was the first one to have this problem, or he will be called as the father of graph theory. The question is, whether is it possible to take a walk and cross over each bridge exactly once? Euler showed that it is not possible. So the origin of graph theory begins with a negative question or a negative solution. There is no way to cross over every bridge without coming back to the same bridge again. So this I can illustrate with the other picture. So here you can see the bridges of Kongsberg and its graph. Island A, Island B, and Island B is connected to Island C by two bridges, and Island B is connected to D by other two bridges. A is connected to C, B, and D. So here, if I start with A, is it possible to traverse each and every bridge exactly once and return to the same point A? So the answer will be definitely no, because if you make a path, you have to cross over, or you have to cross over the bridges twice. Without crossing over to the bridges twice, we cannot make a single traverse. So this is what the solution is. So, or this is what the origin of graph theory is about. So I think with this picture, I move on to the definition of a graph, a simple graph. So here you can see a graph having point A, then B, C, D, and A is connected to B, and A is connected to C, and A is connected to D. Whereas the point or the vertex, we call it as vertex, the vertex C is connected to B with two edges, and the vertex B is connected to D with two bridges. Okay, so which means that this graph is not a simple graph. So by the definition of a graph, we are going to deal with only simple graphs. So let me get into what is a simple graph and what are these type of graphs called. These types of graphs are called pseudographs. That is a graph having more than more or and it or two vertices having more than two edges or multiple edges, otherwise called as loops. That we will see it in detail in the next definition. So here we go for the definition of a graph. So this is what the formal definition of a graph is about. A graph is an ordered triple. So it is an ordered triple, which we denote it by G, and the vertex set is represented by V of G, and the edge set is represented by E of G, and we have a function or that is called incident map that we denoted by I of G. So where the vertex set is a non-empty set, E of G, that is vertex set is V of G, then the edge set is E of G is a set disjoint from V of G, because V of G will have only vertices and E of G will have edges. So both will be disjoint, and I of G is an incident map that associates with each element of edge set G an unordered pair of elements of V of G. Elements of V of G are called the vertices of G, and elements of E of G are called the edges of G. So this is a formal definition of a graph. In the next slide, we can see how this definition is converted into a graph. So here, as mentioned earlier, we can have the vertex V, V1, V2, V3, V4, V5, V6. I put it into the set V of G, having the vertices V1, V2, etc. up to V6. Similarly, we have the edge set that is denoted by E1, E2, E3, E4, etc. It goes up to E8. So I think it is clear to you. Next, we have the edge set as well as the vertex set. Next, we go for the incident map that we denote by I of G. I of G having first incident map E1. So IG of E1, I suffix G of E1. So the edge E1 is connected with two vertices, V1 and V2. Similarly, you can find edge E2 is connected with the other two vertices, V1 and V3. And similarly, you can see this. This is how the formal definition of a graph is defined. I hope this graph is clear to you. Next, I move on. This is called a simple graph. We have the vertex set, edge set, and the incident relation. Okay. Next, types of graphs. A graph G is finite if both vertex set and edge set of G is finite. Finite means you have countable. So the graph, the earlier graph which I have defined here is a finite graph. Since we have 6 vertices and 8 edges, so this happens to be a finite graph. Next, we have a graph with single vertex is called trivial graph. only a point itself, a vertex. If you have a single point, that is called a trivial graph. All other graphs are non-trivial graphs. So I hope this is clear. Next, two or more edges with same ends are called parallel edges or multiple edges. So this is what we have seen in the Kongsberg bridge problem. You can find the vertex B and C and D are connected by, that is, two nodes or two ends are connected with two edges. Okay, that is, same ends will have uh, two edges. Okay, that is called parallel edges, otherwise called as multiple edges. Next, a graph is simple if G has no loops and parallel edges, otherwise called as multiple edges. So the thing or the type of graphs which we are going to deal with this simple graph that will have no loops and parallel edges. So this is what a graph with loop and parallel edges. As I have said, a graph, the vertex V1 has an vertex, or sorry, as an edge that is connected to itself. That is called self loop. So this is a uh, loop, and here the vertex V6 and V4 are connected by two edges. V6 and V4 are connected by two edges that they are called as parallel edges. We will not have these graph. This graph is not simple, whereas our graphs are simple. That is, we don't have loops and parallel edges. Next, a graph with no edges is called an empty graph. So as I have said earlier, a graph with a single vertex is called a trivial graph, or a graph with no edges is called an empty graph. So two graphs G and H are identical. So we are going to see about identical graphs. If the graphs have same vertex set, that is V of G will be equal to V of H, and edges of G will be equal to edges of H, and the function, that is the incident map of G, will be equal to the incident map of H. Whenever you have these conditions satisfied, then those graphs are called excuse me then those graphs are called identical graphs. Okay. Next, we go for a complete graph. A simple graph in which each pair of distinct vertices are adjacent is called a complete graph. So here you can find the vertex V1, V2, V3, V4, V5. A simple graph in which every pair of distinct vertices are adjacent is called as complete graph. That is, V1 is connected to V2, V1 is connected to V3, V1 is connected to V4, and V1 is connected to V5. That is, every vertices are adjacent to one another. They are called as complete graphs. Okay. Next, a graph H is a simple subgraph of G if the vertex set of H is a subset of vertex set of G, and the vertex set of H is a subset of vertex set of G, and the incident map of H is the restriction of incident map of G to E of H. So here we are going to define a subgraph. I will show this with an example. Next, we have one more graph that is called a graph H is a spanning subgraph of G. That is, if the vertex set of G is equal to the vertex set of H. So this we can see it with examples in the next slide. So here you can see a bigger graph. This is a greater graph, and you can have a this portion, a big portion. This is a greater graph, and I am taking a portion of this here in the left hand side. That will be called as a subgraph. Or even if you take a single edge of this graph and denote it by, you can call it as, it has got numerous subgraphs. One such example I have displayed here. Even if a single edge of that graph is taken, it should be a subgraph. or if you take a single point, that is also a subgraph. But the relationship should be, or the vertex set should be smaller than the vertex set of H should be smaller than the vertex set of G. And then edges, we have to take some fewer number of edges, as well as their relationship should be maintained. Okay, this is an example for a subgraph. Next, I go for a spanning subgraph. Here you can see a graph V1, V2 with which is having 10 edges, and the definition, from the definition of a spanning subgraph, all the vertices of the graph G should be present in the subgraph G. So it should have the same number of vertices. So if you take a graph, or I have here in the pink line, the edges that is represented denoted by pink line is a spanning cycle, otherwise called as, or otherwise I can call it as a spanning cycle, since it has got it begins and ends with the same node, or the beginning and the end of that vertex of all the edges will be at the same node. Or even if I disconnect an edge, that will be a spanning subgraph for a given graph G. Okay. Next, we move on to the coloring. Here we have a proper vertex coloring. So what is a coloring? An assignment of colors to the vertices of a graph G so that no two adjacent vertices have the same color. So this is the definition, formal definition of a vertex coloring, that is an assignment of colors to the vertices of a graph G so that no two adjacent vertices have the same color. So here I show this with an example. So here you can see a graph with which is having 6 vertices. As by the definition, we are going to color the vertices, not the edges. So we are going to color the vertices. That should be a proper coloring, such a way that no two adjacent vertices receives the same color. So here V1 and V6 are adjacent, so they are receiving different colors. That is pink and red. Similarly, V6 is adjacent with V5 and V4, so that is receiving a different color, that is green and brown. And V4 is adjacent with V2 and V3, that is receiving a different color, that is yellow and red. So here, by the definition of a proper vertex coloring, we are coloring the given graph G. What is the number of colors used? That is same as the number of vertices. So even though this is a proper coloring, it is a proper coloring, but the purpose of coloring is not satisfied. Or we are going to, if you have 6 edges and if you color 6, if you give 6 colors, then the purpose is not satisfied. That is no, suppose if you have 10 edges, if you give 10 colors, that will automatically will be a proper coloring. But that is not the thing. We have to optimize that. That is the main concept. Or we have to look in for the minimum number of colors to color a given graph G. That will be called as the chromatic number. That is what we are going to do that in the next slide. So here I go for the definition of a chromatic number. The least number of colors needed to color the graph is called its chromatic number, that is denoted by I. So here you can go for this vertex, same graph V1, V2, V3, V4, V5, V6. So there are 6 vertices of the previous graph, the same graph I have taken, whereas in the previous graph I have colored all the 6 vertices with different colors, following the condition that no two adjacent vertices receives the same color. Here again we are going to follow the same procedure. No two adjacent vertices will have the same color, but we are going to optimize the color, or we are going to minimize the number of colors. So here it is just needed blue, red, green. 3 colors are needed to color the 6 vertices. Whereas in the previous graph, which I have shown in the previous slide, I have just given all 6 colors for all the 6 vertices. But this is what the chromatic number. The chromatic number is, we are going to minimize the number of colors for a given graph. That will be called as the chromatic number. Condition that no two adjacent vertices receives the same color. So the chromatic number for this graph happens to be 6, because we need 6 colors, 3, because we need 3 colors to color the graph. Next. we are going to see about one more definition. All these definition and all these basic concepts which I say here will be applicable to the examples which I proceed further in my slides. So for that purpose, I am giving some of the basic concepts that or the concepts which I am going to use it in my application. Next, a click. A click, this is the formal definition. So I just giving the formal definition. If you just read it, a click is an undirected graph G with vertex at V and E. With vertex at V and edge at E is a subset of the vertices vertex at C, which is a subset of V, such that for every two vertices in C, there exists an edge connecting the two. So this is the formal definition. So getting into this definition, you can know what is a click, but I will show this with an example. So note, this is equivalent to the saying that a subgraph induced by C, by the previous definition, by the definition of click, this is equivalent to saying that the subgraph induced by C is a complete graph. So here, next we go for a maximal click and a click number. A maximal complete subgraph is called a click. So a click is different. A click is a complete graph. A maximal click or a maximal complete subgraph is called a click. Next, we have click number. The click number is denoted by omega of G of a graph G is the number of vertices in a maximum click in G. Otherwise, we call it as the order of the maximal complete subgraph. The order of a maximal complete subgraph will be called as the click number. That is, the number of vertices present in the maximal complete subgraph will be called as the click number. I'll show it with an example. So here you have a graph and I'm going to construct a click for this graph. A click should be a subgraph for the given graph as well as it should be a complete graph. From the figure, you can see, I think you can see two complete graphs. That is, one is a triangle having three vertices. It is a complete graph. The other one, the center. So here it is a triangle having three vertices is also a click. But the biggest click should be the maximum subgraph, complete subgraph. That is nothing but the center, this pink colored vertices. This is called K5, a complete graph on 5 vertices. So the order of click number for this graph, that is omega of G for this graph, will be equal to 5. So even next, I go for the vertex independent number. A vertex independent number, this is also a concept. A set of vertices in G is independent if no two of them are adjacent. The largest number of points in a set is called the vertex independent number of G, and it is denoted by alpha of G. So the click number, the vertex independent number are the concepts which I am going to use it in the forthcoming examples. So what is a click number? A click number is nothing but the maximal complete subgraph of G, or the order of the maximal complete subgraph of G is called the click number, and the vertex independent number is denoted by alpha of G. It is nothing but we are going to consider an independent set, a vertex set, an independent set of vertices, or the largest independent set of vertices, such a way that the elements in the set should not be adjacent. So the vertices, it is a vertex set. First of all, it is a largest vertex set containing non-adjacent vertices. Otherwise call it as non-adjacent vertices, because no two vertices should be adjacent to one another. We are going to collect a set of, or a largest set of vertices from a graph G, which will have non-adjacent vertices. That will be called as the vertex independent number, denoted by alpha of G. Similarly, for vertex, we can also have this for edge independent number. The same concept that will be applicable to the set of edges, that will be called as edge independence number. Edge independence number. So this is what an edge independent number. The set of edges in G is independent if no two of them are adjacent. The maximum number of edges in a set is called the edge independent number of G, and it is denoted by alpha dash of G. Vertex independence number is denoted by alpha of G. We are going to see in this presentation, we are going to see only with vertex independence number and the maximal click, that is called the order of a maximal click, that will be called as the click number omega of G. So here, these are some of the properties or the basic theorems which I am going to use it for my application. The first theorem is called for every graph G, the chromatic number, as I have said, chromatic number chi of G will be greater than or equal to omega of G. As we all know that omega of G is nothing but a maximal complete subgraph. So maximum complete subgraph for a complete graph, the chromatic number for a complete graph is nothing but its number of vertices, the order of that graph. So for a graph G, the chromatic number of that graph will be always greater than or equal to this click number of G. Okay, so this is one of the theorem. Next, we go for one more theorem, that is called if G is a graph of order n. So G is a graph of order n, then the statement follows: n represents the number of vertices, that is order divided by the vertex independent number. So that is the chromatic number lies between, the bound is given, chromatic number of a given graph G lies between this order of n by alpha of G less than or equal to that is the order of the graph minus the vertex independent number plus 1. So this is the upper bound and the lower bound for a chromatic number. So these two theorems are very important theorems, or useful theorems, or basic properties of chromatic number theorems. Okay, I'm going to apply these two theorems in the next example. So here I go for a simple and a particular example for a or a simple example for a chromatic number or a graph coloring. So here we are going to see about one simple application, that is two dentists are having new offices designed for themselves. So here in our country there are few problems with the teeth. So dentist will have they are going to have a new office. They are going to design a new office for them. So in that office, whenever we go for some hospitals, we have to wait for so many times. So that is why the name is patient. We have to keep patient and keep waiting for so many times. So sometimes we will be having all the trouble in the body, and then we have to wait for our turn to get the treatment. So here, this situation is two dentists are having new offices designed for themselves. So in that office, in the common waiting room, they have a common waiting room for their patients. So their patients will always be sitting in the waiting room and they will be waiting. So what to do? When will our turn will come? And when we can get the treatment and get away. So similarly, we have to be patient and we have to waiting for our turn. So what they have decided, so it will be sometimes boring, no. So they have decided to have an aquatic area containing fish tanks. So they are going to have some, in most of the hospitals and most of the hotels, I have noticed this, they will be having some of the fish tanks which will have so many varieties of exotic fishes. So those fishes will keep, when we are waiting and looking at those fishes, we will have some peace of mind, or we will have a look at what are these fishes are doing. So it's just an ornamental thing, that's all. So here, next, because so here the dentists have a common waiting room. In that common waiting room, they have decided to have an aquatic area containing fish tanks. So in those fish tanks, they are going to have some beautiful varieties of exotic fishes. So all those fishes will be of different colors, different natures. Some will be fighting, some will be aggressive. Some fishes don't like those climate. They don't like some cold water. Some will be having some moderate tropical conditions. All these conditions they have to take into account, because even though I have this experience of growing fishes in tanks, so all those fishes, this tiger fishes and all, they will kill all the small mollies. They will die, black molly, white mollies, all will die. And these gold fishes are very soft. Similarly, fighter fishes, some fighting fishes will have different colors. No, they look attractive, but they will kill all the fishes. and some fishes will be called as tank cleaners. They will be sitting at the bottom of the tank and they will be eating all the other things, all the waste things. So here they have decided to have a tank containing all such kinds of fishes. So we have to put those fishes into tanks such a way that in such a way that that one fish should not harm the other fish. There are some fishes that will harm the other fish. Similarly, certain fishes will have their food that will not be applicable, that will not be admitted for the other fish, the other varieties of fishes. So these are all the conditions they are going to take it into account. So next, it is decided to have, what they have decided, we will have 9 varieties of exotic fishes. So those fishes will be denoted by F1, F2, etc. F9, 9 varieties of fishes, where fishes that cannot be placed in the same tank or F1 and F2, if they have a common character, they can be placed. If they have abnormal characters, they have to be placed in the different, they should be placed in a different tank. So what they have decided, they are going to have 9 different varieties of exotic fishes, and they have they are going to have the minimum number of tanks. They have to place this 9 fishes into the same tank, as they have to minimize the number of tanks. Okay, so here we have some relation. So fish 1 cannot be placed with fish 2, fish 3, fish 4, fish 5, fish number 6, and fish 8, because they don't have common characters. They get what to say, they cannot be placed because fish 2 will be aggressive for fish 1. Similarly, the food fish 3 eat will not, fish 1 will not eat the same kind of food. So these are all the different classifications. Similarly, fish 2 cannot be placed with the same fishes F1, F3, F6, F7, and it goes on. So all the 9. F3 cannot be placed with these 4 types of fishes. F4 cannot be placed with 1, 5, 8, 9. F5 cannot be placed with 1, 4, 8, 9. F6 cannot be placed with 1, 2, 3, 7. Similarly, I have given this. So what is the thing is that these are the 9 fishes, and all these 9 fishes, the relation, exotic fishes relations. F1 cannot be placed with these kinds of fishes. F2 cannot be placed with these group. F4, F5. I hope you can see from this slide. So the question is, what is the minimum number of tanks required? What is the minimum number of tanks required to place these 9 exotic fishes? What is the minimum number of tanks required to place this 9 exotic fishes? So here I go for the graph. So here, from the condition given, F1, fish 1 cannot be placed with fish 2. So we are having an edge, common edge, or fish 1 and fish 2 are adjacent because they should be placed in a different tank. Fish 1 cannot be placed with fish 2. Similarly, from this relation, we are forming a graph. Fish 1 will be connected to fish 2, fish 1, fish 3, fish 4, fish 5, fish 6, fish 8. Okay, so here, so I have drawn a graph. So the graph shows fish 1 cannot be placed with fish 2, fish number 3, and F1 cannot be placed with F5, F8, and F4. Similarly, F6. So this is what the graph which we have formed. So these are all the fishes. All the 9 fishes are represented by a graph. The graph represents whenever they cannot be placed in the same tank, they have an edge joining them. So which means that they should be placed in a different tank. Okay. So here, from this graph constructed, you can see what are all the things you can see is that there are 9 vertices. Okay, there are 9 vertices, and there are edges connecting according to their relation. Now, what is our idea is, what is the minimum number of tanks in which we can place all those 9 fishes? Okay, so the thing is, we are going to find a chromatic number for this graph, and then how this chromatic number is related with the click number, that is omega of g, then the vertex independent number. So from the next slide, you can see that this is the click. So I have drawn with the green line, that is F5, F8, F9. Okay. Here you can find a triangle. The triangle, this is a click. Similarly, even though this is a click, this is not a maximal click because a greater click exists. That is, if you look at this uh, vertex F2, F6, F3, F7, here you can form one more click. This will be called as the maximal click, whereas this is, even though it is a click, it is not a maximal one. So this is the maximal click having 4 vertices. So obviously, a maximal click having 4 vertices is nothing but a complete graph on 4 vertices. The chromatic number for this graph will be 4. Definitely, it will be equal to the number of vertices, 4. So I have given 4 different colors for this click: red, green, blue, yellow. Okay. Similarly, in order to have a whole coloring, in order to give a whole coloring for this graph, we should have more than 4 colors. From the click itself, there will be more than 4 colors needed. We should have, it should be chromatic number is always greater than or equal to omega of G. So it will be either equal to 4 or it will be more than 4. Okay. So I have, this is a click having 4 colors, and I have also given a coloring for this graph. You can find the number of colors or the minimum number of colors to color this given graph happens to be blue 1, 2, 3, 4, 5. Is it right? Am I right? So here we go for, or we refer to the theorem now. What is n? N is the number of vertices. They are nothing but the 9 fishes. And omega of G is the big number, that is equal to 4. And here we are going to consider the alpha of G. Alpha of G is nothing but the vertex independent number. From the definition of vertex independent number, it should be a vertex set for this given graph. The vertex set for this given graph having non-adjacent vertices, that should be the maximum number of non-adjacent vertices. So the maximum number of non-adjacent vertices for this given graph will automatically be 2. You cannot have more than 2 vertices in the vertex independent set. So suppose, for example, I can say if you take F1 as the first vertex, then you can take the other vertexes F7. So this is the 2 vertices which you can accommodate, or which you can have it in the set of vertex independent set. Either you can go for F1, F7. Otherwise, if you don't want F1 and F7, you can go for F1 and F9. That will be the F1 and F9. At the maximum, you can only accommodate 2 vertices. Okay. So here, the order of the given graph, that is the number of fishes, that is the number of vertices 9, and the chromatic number, and the omega of that graph will be equal to 4. The vertex independent number of the graph will be equal to 2. And by the theorem 2, you have this chromatic number will be greater than or equal to n by alpha. N by alpha of G, that is 9 by 2. Similarly, 9 by 2 will give you 4.5. That is greater than or equal to 4.5. Thus, the chromatic number for this application, for this graph, happens to be 5. So chi of G will be equal to 5. 5 colors. They represent. We need 5 different times to place these varieties, 9 different varieties of exotic fishes, such a way that we are going to optimize. We have optimized the cost of constructing the tanks to replace 9 different varieties of exotic fishes in order to attract the patients. Okay, so this is a simple practical example. Suppose if you look at this example as an ornamental thing, that is nothing, that is an ornament, or it is only an attractive thing. If you apply the graph theory idea, then that becomes an application. Okay. Similarly, I proceed with the other application. This is called, I call this application as a COVID-19 class scheduling. Or here, nowadays we are at the time of strange corona days. So when the classes will open for children, or when the colleges will reopen for our students, so there is a big issue, and there are few things that we have to follow. Is that we have to keep social distancing. So for that purpose, I just apply this example. Okay, so I call this as COVID-19 class scheduling example, something like that. The idea which I thought, I just apply it as a graph. Okay, so here you can find the problem at a gathering of 8 teachers. So there are 8 teachers, and each teacher will be teaching several subjects. They are not going to teach the same subject. They will be teaching English, maths, physics, chemistry, biology. What are all the things you have of an institution? They are going to teach 8 different subjects, which we denote by C. So we are going to classify the 8 teachers into a set C. They are going to have A1, A2, A3, A4, A5, A8. 8 teachers are there. So here, next condition, it is decided to have 3 teachers for a class to teach several subjects for 7 different classes. So here we have 7 classes. So we are going to conduct 7 different classes in the morning. There are 2 shifts. I organize this as shifts. The first shift in the morning session, and the second shift in the afternoon section. Okay, so here we are going to have 8 teachers. 8 teachers will teach 8 different subjects, several different subjects, and there are 7 classrooms. There are 7 classes to be conducted in one shift. There are 7 different classes to be taught at a shift, and each class will have 3 teachers. So at the maximum, if you take C1, class 1 will have 3 teachers, A1, A2, A3. Similarly, if you go for second class C2, denoted by C2, C2 will have 3 different subject teachers. And we have to find a time schedule or a period in which you have to conduct this 7 classes in the forenoon section. That will be called as a first shift. Similarly, in the afternoon section, you can go for the other second shift in order to keep social distancing of students present inside the classroom. Because suppose if you have 60 students, keeping 60 students in a class will never going to be it will be an issue on maintaining the social distancing. So in order to reduce those or in order to maintain social distancing, we are going to reduce the strength of students in a class such a way that the first 30 will be in the forenoon and the second 30 will come to the afternoon session. Okay, so this is what I'm going to say. The 7 classes selected for this purpose are C1, and you have 3 teachers, A1, A2, A3. And the second class C2, you have teachers A2, A3, A4, C3, A4, A5, A6, C4, A5, A6, A7, C5, etc., C6. All those teachers, 3 different subject teachers going to particular classes are denoted by this set. Okay, so here you can observe that there may be few teachers who might be getting into the same different classes, or C1 has a teacher A2 and A3. The same teacher is being or she has to go to, or he or she has to go to the other class C2. C2 has, or there is an overlap. You can see that a single teacher may opting to go for more than 2 or 3 classes. So there should not be overlapping of teachers at that particular interval of time. So C1 has teacher A1, A2, A3. Similarly, if you look at C2, C2 has teachers A2, A3, and A4. Here you can find that teachers A2 and A3, A2 and A3 are going for two classes, C1 and C2. So the thing is, C1 and C2, class 1 and class 2 should not be conducted at the same time, same period of time. If they are conducted at the same period of time, then those teachers will get clashed or overlap, their periods will get overlapped. So here also, similarly, teachers in C2 is the class and C3 is the other class. Here you can find some A4, the teacher A4 goes for C2 as well as C3. Similarly, teacher C4 goes for class A6 and A6. Sorry, teacher A6 goes for C3 and C4. Likewise, you can observe from the set C5, that is teacher A1 goes for C1 as well as for C5. Similarly, teacher A1 is present in C6. And similarly, for the class C7, teacher A2 is present in C2. So we have to avoid this overlapping condition, as well as we have to find a shift for conducting the 7 classes having 3 different subjects, and they are having 8 teachers. So here the problem again, if each class is to meet during one of the time periods, the time period is given. The time period for the class is from 8 to 9, 1 hour, 9 to 10, 10 to 11, 11 to 12, 12 to 1. This is the first shift. So here you can find 5 hours, 8 to 9, 9 to 10, 10 to 11, 11 to 12, 12 to 1. Then what is the minimum number of time periods needed for all 7 classes to function? So here we are going to find the minimum number of the shift time period for the 7 classes to function. Okay, so here the condition, the solution here comes. No 2 classes can meet during the same period if some teachers belongs to both classes. So this I have explained it before. No 2 classes can meet during the same period if some teachers belongs to both classes. Now I'm going to define a graph whose vertex set will be V of G, that is denoted by C1, C2, C3, C4, C5, C6 and C7. They are nothing but 7 different classes. All the 7 different classes will have 3 teachers. There may be some teacher, they might be going for C1 and C2. So if you have a common teacher present in C1 and C2, then you have to connect that by an edge. Okay, the 2 vertices Ci and Cj are adjacent if Ci intersection Cj should not be equal to empty set. And so we go for this graph. Okay, so this is the graph. C1, you can find C1 is adjacent to C5, which means that a particular teacher in the class C1 will be going for this class C5 also. Similarly, C1 is adjacent to C6. A particular teacher in C1 will be going for C6 also. Likewise, C1, C7, C1, C2. Next, all the 7 classes are denoted by 7 vertices: C1, C2, C3, C4, C5, C6, and C7. Okay, so now I have given, we have constructed a graph using the condition given in the vertex set of C1, C2, C3, etc. up to C7. This is the graph which we get. Okay, now we are going to color this graph. As usual, if you give 7 different colors, then there is nothing to prove, there is nothing in it, even though the condition adjacency vertices receives same different colors. But we have to find the minimum number of colors needed to color this simple graph. Okay, so the thing is, here you can find, as I have said with the previous example, for this problem also, we are going to look into the number of vertices, that is n. Next, we are going to look into the omega of G, the quick number of this graph. Finally, we will go for this alpha of G, vertex independent number of this graph. And from that, we can find the chromatic number. So the chromatic number will be the time period in which we can schedule all these 7 classes in the time period. The time period given here is from 8 to 1 o'clock. There are 5 hours there. So what will be, we can, is it possible to use those 5 hours, or still we need a few hours less than this 5? So we are going to look into this. So the next graph will show you. So here you can see this is a click. So what is that? A triangle. This is the click marked with the blue line. So now, since this is a maximal click, you need 3 colors. The chromatic number will be greater than or equal to 3. Now, to color this graph, we are going to give 1, 2, that is blue, green, red, yellow, 4 different colors. Okay, and next we are going to say about this alpha of G, that is vertex independent number of G. So what is the vertex independent number of G? You can go for, it should be a largest set of vertices having non-adjacent vertex of the given graph G. So here the total number of vertices n is 7, and the click number, the maximal complete subgraph present in the given graph G is 3, and the vertex independent number alpha of G will be 2. So only 2 vertices can be present here. You can go for any such 2, they are non-adjacent. Suppose if you take for C5 and C2, they are non-adjacent. So if you take these vertices, that will be either you can go by C2, C5, Otherwise, you can also go by C6 and C7, these two. If you take this group, they are non-adjacent. So that will be true. Then accordingly, n by 2 will give you 3.5 greater than or equal to 3.5. So which is 4. So we can schedule these 7 classes in the in the 4 periods. That is in the morning shift. Okay. 4 hour chromatic number will be greater than or equal to 4. So here you have the chromatic number for that graph equal to 4. So the question is, this is what I have said. All these things I have written. So alpha is 2. Since there is a 4 coloring of graph as shown in figure, it follows that chromatic number will be equal to 4. Hence, the minimum number of time period needed for all the 7 classes to meet is 4. Accordingly, we can have the resulting scheduling of classes. 8 to 9 C1 will be conducted, and 9 to 10 8 to 9 C1 C4. 9 to 10 a.m. you can have C2 C5, 10 to 11 C3, 11 to 12 noon you can conclude C6 and C7 for the first shift. Similarly, you can go for the other shift, and this is what a simple example which I thought of it. Even though they might have some drawbacks, that we have to look into this when we get into the practical mode. Okay, so this is one application. Similarly, I have one more application also. So I think almost a hour has been crossed. So I just say the problem, and I just move on with the slides. At a regional airport, there is a facility that is used for minor routine maintenance of aeroplanes. So this is also a beautiful example. Here we are going to see the time as well as the work is equally distributed to all the workstations, because here in this example, the time schedule is from 7 a.m. to 7 p.m. and we are going to service some aeroplanes, all the aeroplanes. There are 4 service locations here, 4 service locations, and all these 4 service locations will service their aeroplanes, and the time schedule is from 7 a.m. to 7 p.m. and they have to maintain for each and every flight, they have to maintain some routine checks, otherwise then there will be a big problem. Okay, so performing this maintenance requires this time, if you want to service an aeroplane, you require approximately 2.5 hours per plane. I think we can go take it as 3 hours per plane. However, 3 hours are scheduled for each plane. Okay, so 3 hours is needed for a workstation to service an aeroplane. There are 4 service stations. The work schedule for these 4 service stations is from 7 a.m. to 7 p.m. Okay, so a certain location may be scheduled for 2 different planes if the exit time for one plane is same as the entrance time for the other plane. So this is what the conditions are given. Yes, same service location can service 2 planes, because one plane will be leaving the service, the other plane will be entering the service. That is allowed on a particular day. So here on a particular day, 12 aeroplanes are require this maintenance schedule. So we denote that planes by P1, P2, etc., P12, or the schedule for maintenance during the indicated time periods. So here the time period is indicated. Plane 1, the time period for their servicing is 11 a.m. to 2 p.m. and plane 2, 3 p.m. to 6, plane 3, 8 a.m. to 11 a.m., plane 4, 1:30 p.m. to 4:30. Likewise, the time schedule is given. So with this time schedule, I think I can move on with this application. So it is similar to that. Okay, so I just go for this diagram. There are 12 planes, and these planes, plane 1 and plane 2 are connected. Since there is an overlap of that time period, suppose the service time is 1 to 3 hours, 10 to 12, then 11 to 12, 11 to some period will be for this plane 2. So if they have an overlapping in their time period, then they will be connected by edges. Okay, so what is the, now our time is, all the 4 service stations should get equal number of planes, because a particular service station cannot get more number of planes serviced at the same time. Okay, so they should have some equality in their work share. So to define this, we have constructed a graph following these previous conditions, these time scheduling conditions. If there is an overlap in the time period, then those vertices will be adjacent. If there is no overlap, then they will be non-adjacent. Okay, so here the next slide. Here again, once again, I'm going to get a maximal click. So here you can have 1, 2, 3, 4 vertices, K4, complete graph with 4 vertices. The chromatic number will be definitely greater than or equal to 4. So also omega of G, order of the graph will be equal to 4. And you have the color class. Okay, so here you can see 1 blue color appears, red color 2, blue color 1, 2, 3, 4 colors. So we have given 4 colors, and we are going to group those 4 colors into color classes. Color classes are nothing but the vertices having same colors will be grouped into a single color class. For example, if you look at P1, P3 and P6, it has got blue color. So this becomes one color class. Similarly, the other red color class, P2, P5, P10. So I have grouped that into the other color class. And yellow color, P4, P8, P11, that is one particular color class. Similarly, the remaining color class will be red, P2, green color class. That is for the color green, you have P2 and P9. So this is what the scheduling is all about. And you can have each and every service station will have 3 planes serviced at that particular time. So it is ideally it will be good if each color class has the same number of vertices, namely 3, so that each maintenance crews services the same number of planes during the day. So all the service station will service minimum. All the service crews will get 3 planes in out of those 12. So 4 into 3, 12 planes will get serviced on this particular time schedule. So a 4 color is required, and though we have split those 4 colors into 4 color classes, P1, P7, P11, and P12, that induces a click. So all these 4 service stations will be servicing, each will be servicing 3 planes. Okay. Next, one more application, that is, now I go on to the other topic that is called as harmonious chromatic number. A harmonious coloring is a proper vertex coloring in which every pair of colors appears on at most one pair of adjacent edges. So earlier we have seen about simple graph colorings. Now we are going to see about this harmonious coloring. A harmonious coloring is a proper vertex coloring. The condition induced here is every pair of colors appears on at most one pair of vertices. So here, this is the condition. Every pair of colors appears on at most one. At most means at the maximum, there should be only one pair. If you give 1 and 3, this 1, 3 should not be repeated. Whereas in ordinary coloring, this 1, 3 pair can be repeated. But this harmonious coloring, a pair should not be repeated more than once. And the harmonious chromatic number, as I have said, will be the minimum number of colors needed for any harmonious coloring of G. So this is the formal definition. The first paper appeared on 1982 by Frank Harare and M.J. Planck. The proper definition is due to Applecraft and S.M. Krishnamurthy in 1983. So next I give an example. So here you can see a proper graph coloring example. 1, 4, 1, 3. So this 1, 4 pair will not be repeated anywhere else. Similarly, this 1, 3 pair will not be repeated. As such, a pair should appear only once. Okay, at the maximum it should appear only once. And we have to minimize the number of colors. So here at the maximum, the harmonious chromatic number for this graph happens to be 8. So such a way that you can harmoniously color this particular given graph. Still, I move on with some examples. Few examples on harmonious coloring. 1, 2, 1, 3, 1, 4, 1, 5. And the harmonious chromatic number for this graph is 7. Also, I just skip these examples. All these are harmonious coloring example graphs. Next, one interesting conjecture on harmonious coloring. The harmonious chromatic number of a central graph of a complete graph Kn. So this is one interesting conjunction. So chromatic number for a central graph of Kn will be equal to this value. We will see it later. What is a I hope that you understand what is a complete graph, and the central graph I have not defined. We will see it later. So these are all some of the results published on harmonious chromatic number. For a graph G, the harmonious chromatic number will be delta. Capital delta is nothing but the maximum degree. N represents the number of vertices or the order of that graph. The chromatic number for a graph G will have this value. This result is due to Lee and John in 1987. They have got a bound. Similarly, the other bounds you can see for any graph G with diameter 2, then this is one of the general bound. Chromatic number of G will be equal to N. So all these results are due to this Sim, Lee, and John Mitchum. Other result, again, the upper bound which we have seen here was again sharpened, or he made some sharp bounds. This is Liu. For any graph G, chi of G will be less than or equal to 2 times delta lower bound. This is ceiling function of the graph, order of the graph N, square root of order of the graph N. Similarly, these are all existing results or literature or the bounds that exist for harmonious chromatic number for different. This is for general graph. This is Cartesian product of two graphs H and G, where this Pn is a path on n vertices. Then the Cartesian product of Pn into Pm will be less than or equal to 12 times ceiling function of n into root m. And the other, for complete binary trees, this value holds 6 times ceiling function of root of 2 power m minus 1. So here I have defined the central graph. For a given graph G, we are going to do a graph operation. That is nothing but we are going to subdivide and every edge of a given graph G exactly once, and then join all the non-adjacent vertices of G, which were previously adjacent. So here, this is an example. I just draw it here. Each and every edge will be subdivided, and the original graph, the non-adjacent vertices should be made adjacent. So this is the definition for a central graph. Okay. So why we have defined this central graph is it has got beautiful properties called graph embeddings. So here, the graph which I show here is central graph of C19. C19 is a cycle with 19 vertices. If you construct a central graph for the cycle of 19 vertices, okay, C19 is a cycle on 19 vertices. If I construct a central graph for this cycle that is represented by C of C19, it embeds a red graph. This is called Greenwood-Glenson graph. It should be a 5 regular graph on 16 vertices. So the pink lines represents a 5 regular graph on 16 vertices. The name for that graph is called Greenwood-Glenson graph. So this graph has been embedded or a subgraph for this central graph. Similarly, one more example, same cycle with C19, central graph of C19 embeds a 4 regular graph on 19 vertices that will be called as Robertson graph. So Robertson graph is a 4 regular graph on 19 vertices. Next, what are all the bounds which we have obtained for the harmonious chromatic number of harmonious chromatic number? So for a total graph of cycle, we have this chi h of t of cn will be less than or equal to 4 plus n. Similarly, the other result for the middle graph of cycles, harmonious chromatic number of m of cn will be less than or equal to 2 times root q. Here q represents the number of edges in the middle graph. Okay. Next, other bounds, chromatic number of mn will be equal to m plus n. Okay. The other bounds I just move on. I think I have taken a lot of time. So finally, these are all the results which we have obtained. And the interesting conjunction on n regular graphs. This conjecture, you can go through it. And finally, to conclude, I go for a practical example for this harmonious coloring. So this is an example on harmonious coloring. So far we have seen examples on chromatic numbers or a graph coloring, simple ordinary graph, proper vertex coloring. Now I'm going to say an example for a proper harmonious coloring is also a vertex coloring. The condition is the same condition. No two adjacent vertices should have same color, but the few more condition imposed is that is a pair of colors should not be repeated more than once. So if you assign 1 4 or 1 3, this 1 4 or 1 3 combination should not be repeated again in the graph. So this is the condition for harmonious chromatic number, and we are going to find the minimum number of colors to color a given graph G. Okay. So what is the application? What is the practical application for this? So here you can see a practical application besides a satellite navigation system. So I just I just don't want to read these things. One one incident or a real incident happened in the year 1983 or 87. This I am not sure about this year. I think it should be 1983. So which I have watched it in the National Geographic Channel. There is a program called Air Crash Investigations. So many times I used to watch that program, Air Crash Investigations, because I will be liking many programs on aeroplanes, jet fighting planes, etc. That's why I placed one example on this plane scheduling. So here in the year 1983, there is an incident that happened in the Indira Gandhi National Airport, which I have witnessed or which I have watched in the National Geographic Channel. So at that time, there were two aeroplanes. I hope there are three aeroplanes that were approaching for landing at the international Indira Gandhi National Airport at New Delhi. So they were approaching the airport for landing. One flight is the US Army flight. So there will be one pilot is inside that flight. He is from US Naval flight. The other two are passenger aircrafts. One is from, I hope, one flight is from Saudi Arabia. The other one is from Russia, I think so. There are three different aeroplanes. They are approaching for landing at the international Indira Gandhi National Airport. So there will be an air traffic controller inside the control station. He will be communicating with all the pilots in the three different planes, because he will be giving the instruction for them for when to land and when they should land, at what altitude they should land, something like that. What is the weather condition there, etc. So he was giving the he is handling three aeroplanes at the same time. He was giving an instruction for a particular plane. You should fly at this altitude and you should descend now, or your arrival time, your landing time is this time. So he was giving clear instructions to them. Okay. So what is that? The military pilot is driving, he's on a flight, and the other two passenger flights were also approaching the airport. They are all controlled by a single air traffic controller. He is communicating all the three flights. So this is the situation. So this air traffic controller has given some instruction to a pilot in the Saudi Arabian Airlines, saying that he should be flying at such altitude, 500 or something like that. He should be flying at some different altitude. And similarly, he is giving some instruction to the Ukraine airplane, something Russian, that is Russian Airways, something like that. He is giving some other altitude for that plane. So suppose if both planes come at same altitude, they will clash. They will crash. Okay. So he was instructing a different altitude for the first passenger flight and a different altitude for the second passenger flight. But there was a communication problem. That is the language which the air traffic controller speak accent. So we will all have different accents. Sometimes which I pronounce may be differently heard on the other part. So the same kind of problem happened, and these two passenger aircrafts were flying at the same altitude and they got crashed. This was a very great tragic incident that happened. So at that time, there were no advanced air traffic systems. Or nowadays, if two planes fly at same altitude, there will be some indications. There will be so many alarms are there. But at that time, there is no alarm to indicate that both planes are flying at the same altitudes. Okay. So as well as there was an investigation going on whether this air traffic controller made some mistake in communicating with those two pilots. But nothing like that happened because he was giving a different altitude to both the pilots. But the pilots misunderstood that with the accent. So because there will be some Saudi Arabian accent will be different and our accents will be different. So such kind of incident happened and there was a great tragic happened. So in order to avoid this, there is one application for harmonious chromatic number is there. Here, now the state authorities have decided to install a very high frequency omnidirectional range radio beacons. So the purpose of this beacons is they will be having passing different frequencies or different frequency or different altitude directions that will be given and that will be detected by the airplane system. They will if they fly at the same altitude. So this is very costly. Installing a radio beacons will be very costly. So we have to minimize the number of radioactive beacons. For example, here you can see this is the airport and there are 4 different planes approaching the airport for landing. So if they land, uh, this is one color, blue, red, green, and pink. They are landing the airport. The air traffic controller will be communicating with all the 4 pilots and he will be instructing for them to maintain different altitudes. So in order to check whether those flights are maintaining different altitudes, the state authorities have decided to install some beacons such a way that each and every flight fly at different altitudes. So installing these beacons will be very costly, but we have to minimize the number of beacons for this purpose. So we are going to construct a problem. To identify the current position of a plane, one has to measure the signals of 2 VOR radio beacons. So 2 will be because 2 radio beacons will have 2 different values, 1413. Okay, 1314. So this is what I have said. For safety reasons, 2 proximate beacons cannot be sending signals of the same frequency, and now 2 different airlines can have different beacons sending same signals on their terminal nodes. So let us hypothetically assume that the state authorities decided to modernize the existing network of radio beacons. In order to reduce the cost of this enterprise, they decided to install a few types of beacons as possible. The question is, the following 2 questions arise. How many beacons of each type are needed? Where should the beacons be located at ground level? So we are going to install beacons. With the help of that beacons, we can find different altitudes and no 2 beacons will be receiving or sending the same signal. Okay, so now if we find the chromatic number for that graph and its optimal coloring, then the harmonious chromatic number will be exactly the number of various types of beacons requested by state authorities. Okay, this is what an example for harmonious coloring. Right, I think I can conclude with this example. Anyway, I thank the management and the organizers and all the faculties who are engaged in organizing this webinar on graph coloring. And I thank, being an alumni of Kungunadu Arts and Science College, I thank all the organizers, the management and the secretary madam and the principal of Kungunadu Arts and Science College. I also thank the head of the department, Dr. V. Gokilavani madam, and the organizer, Dr. Ravichandran. And also I thank the coordinators, Vivek and Prakash, and all the faculty members for giving me an opportunity to share some of the thoughts which I have learned on graph theory. And all these examples, few examples were taken from King's handbook, chromatic number and chromatic graph theory. It's a very good book to refer. Thank you very much. If I have taken a few time, I just apologize for taking your time, and thank you very much. Thank you.
Myself, Dr. E. Prakash, Assistant Professor of Mathematics. It's my privilege to deliver the vote of thanks. First, I would like to express my sincere thanks to our President, Dr. M. Arachami sir, and beloved Secretary and Director C.A. Vasugi ma'am for giving the opportunity to organize the Alumni Webinar Lecture Series. And I would like to thank our Principal, Dr. M. Lakshmanasamy sir, Dean Academics, Dean R&D, for their support and guidance in the executing this program. I thank our today's chief guest, J. VERNOLD VIVIN, Assistant Professor of Mathematics, University College of Engineering, Nagargoil, for his interesting and informative talk on chromatic numbers and its applications. Thank you very much, sir. I would like to thank Head of the Department, Dr. V. Kokilavani ma'am, and all other faculty members for taking effort in organizing this webinar. I thank all the participants for making this event a great success. Thank you once again. Thank you.